So a tube closed at one end and containing air is excited. Is excited. Oh, I think we solved this question before. Oh, yes. 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 I think one of the answers is okay. I think is this question. So an open pipe resonates with a tuning fork of frequency. An open pipe resonates with a tuning fork of frequency 500 hertz. It is observed that two successive nodes are formed at distances 16 and 46 centimeters. It is observed that two successive nodes are formed at distances 16 and 46 centimeters from the open end. The speed of sound in air in the pipe is the speed of sound in air in the pipe is okay. So hold on with the question. I just observed that we must go through resonance tube properly in order to apply. So yes, you hold on with solving the question whilst we go through resonance tube extensively. So the resonance tube experiment is actually an experiment that is used to determine velocity of sound in air. That constant value of velocity of sound in air, which is usually around 330 meters per second. If we want to confirm that theoretical value, we use the resonance tube experiment. This experiment, you must be doing it in school. It's a simple experiment. Now, the materials for the experiment includes, we have resonance tube. The resonance tube which is just like the burette used in chemistry titration. Then you have the tuning fork. The tuning fork is just like the fork. The only difference is that if you have not seen a fork before, this is a fork. Now, the tuning fork has only two prongs. You see, here there are four. 1, 2, 3, 4. But for the resonance tube, these two in the middle are not there. You only have these two prongs. We call them prongs, P-R-O-N-G-S, but they are longer. Now, the tuning fork produces a wave with only one frequency. So different tuning forks have different frequencies, meaning when you strike and they vibrate, they produce wave of only one frequency. Okay. So you have the resonance tube, which is just like the burette. You have water or liquid, any other liquid is used to fill the tube. Now the whole experiment is like this. So the diagram is like this. Gerald, did you perform the resonance tube experiment?
No, sir.
Hey,
So they didn't even teach us. So,
okay.
but I still a good school. So,
I have not said anything. Anyway, there is the enormity of work. These days is some way. So it's just a tube like this. This is a tap. This is a tap. Now, we fill the tube with water. So I'm assuming this is water filled to a certain level. The rest is length of air column. So from the open end to this side is the length of the air column. Then the tuning fork which is like this, just like the fork I showed to you. Gerald, do you know experiment on a resonance tube came in or B? In
yes,
what?
sir. Said that was my alt.
Yes, what's the practical?
Yes, sir. Said that was my alt.
Ah, okay. So this is the tuning fork. Now the function of the tuning fork, as I said earlier, is used to generate wave of one particular frequency. So different tuning forks have different frequency, meaning, and how it is used to generate the wave is that, you see, if this is the tuning fork, then there is a gum-like or something elastic, okay, something like the cork. So you need to strike the tuning fork against the cork, and it will create wave. Okay, now you realize that the prong will be vibrating. When you send it close to your ear, you hear a vibration of the prong. The prong creates wave of one particular frequency. Now, in this experiment, all that we want to create is that we want to create cause resonance. And what is resonance? Resonance is when one vibrating medium or particle, a particle vibrating at its natural frequency, affects the frequency of vibration of another. Okay, now as I'm speaking to you, you could hear me loud and clear due to resonance. What is happening is that as I speak, my vocal cords, that thing over here, what you call as Adam's apple, when you speak, touches, vibrates. So whilst it vibrates, there is air column there's air within my throat. So if the vocal cord vibrates, it sets the air within my throat to also vibrate. Now, when the frequency of vibration of the air matches the frequency of vibration of my vocal cords, we say resonance has happened. So resonance or forced oscillation. I'm forcing you to oscillate as how I oscillate. That's resonance. Resonance or forced oscillation occurs when one particle vibrating at its natural frequency affects the frequency of vibration of another. Let me write something for you. Resonance or forced vibration occurs when a particle vibrating at its natural frequency affects the frequency of vibration of another. So when I force you to vibrate as how I vibrate, that is resonance. And every resonance is characterized by loud sound. You see, so when my vocal cord vibrates and I affect the air particles around within my throat and around my mouth to vibrate as my vocal cord, okay, resonance is said to have happened. Now, every resonance is characterized by formation of loud sound. So, because I am forcing the air particles within my throat and then around my mouth to vibrate, the reason for which you could hear a loud sound, which is my talking. So once you could hear me speak, it means resonance is happening. Okay, so with this experiment, all that we want to do is that we have a vibrating body, which is the tuning fork, vibrating at its own frequency. Now, we cause it to vibrate and then bring it close to the open end of the burette or the resonance tube. What we want to achieve here is that we want the air particles within to respond to the frequency of vibration of the tuning fork. So the air particle or molecule, the air molecule in the tube is made to resonate with the tuning fork. And when the air particles within the tube simply resonate with the tuning fork, we say that the two are communicating, or the two are vibrating with the same frequency. Now, a particular length of the air column would cause this. So we want to vary the air column by opening this tap for water to flow out. Okay, so a particular length which is not known would cause resonance to happen. So there must be a tap so that we can regulate the water level in the tube. So we can have that length which would cause resonance to occur. Adwa ekwia watma ekwia doma inshira oye Josephine, and then please, do you understand? Are you following?
Yes, please.
Okay, so that is the reason why we have this tab, so that we can always adjust the length of the air column within the tube. Now, you see, when I cause water to flow out, I'm increasing the length of the air column. So if it is here, and I open the tap for water to drain out up to this level, it means the length of the air column is increasing. So this would be the length of the air column if it is open. So the more you drain out water, the larger you have as the length of the air column. Please, is there any question before I continue? Ekweadom, are you there?
Yes.
All right. Now, after opening the tab, and when resonance occurs, I note that the resonance tube occurs work on the principle of closed pipe. Closed pipe, we have one end closed and the other end open. So for closed pipe, we have this. Okay, there's the open end, and then there's the closed end. In the resonance tube, the water bait, the meniscus of the water serves at the closed end, whereas this side serves at the open end. So it works on the principle of closed pipe or tubes. Now, when the water level, there can be one or more positions of resonance, meaning there can be one or more lengths of air column where resonance would occur. The first one is the first position of resonance, and that is the first harmonic in closed pipe. After obtaining the first position of resonance, if you continue draining out water, and then whilst the tuning fork vibrates at the open end, there can be another position of resonance. The second one is the second harmonic. Okay, so let's see how we can use this to identify or obtain velocity, or to confirm the velocity of sound in air. So assuming that whilst I drain out this, I heard a loud sound at this length of the air column, which when measured from here to here is L1. Then it means this is the first resonant position. First resonant position or length. Now, under closed pipe, the first resonance, if you have L length of the tube, is drawn as when there is no end correction. It's like this. There is always antinode, node at the closed end. So those things. So the first harmonic is always like this. So L, the length of the air column is equal to the wavelength of the wave, which is quarter lambda. Okay. Therefore, lambda is equal to 4L. And the first harmonic, F1, is equal to V over lambda 1, which is V over 4L. We will use the same application to also derive this. Now, if there are two positions of resonance, meaning when this is vibrating and when you drain out up to this level, you heard a loud sound, then that represents the first position of resonance. In that case, the first harmonic is always equal to L1. L1 is equal to quarter lambda. This is without end correction. Without end correction. If there is end correction, then this is how it will look like. Let me extend it a bit so that we'll use this as the meniscus of the water. If there is end correction, you know that the antinode would extend beyond the open end. So this becomes the end correction E, and the length of the pipe, the length of the air column becomes L1. So if there's end correction, then we'll say that quarter lambda is equal to L1 plus the end correction. Okay, so this is the expression for the first position of resonance. First position of resonance. Okay, now if there is a second, by continuing to vary the water level, and you hear a second sound, it means you have a second position of resonance. You can compare the two to determine the velocity of sound in air. So when there is a second position of resonance, then the whole diagram this time becomes there's a meniscus of water, there's a water level. Now, the tuning fork vibrates to create the resonance, where the air molecules respond to the frequency of vibration of the tuning fork. And don't forget, the second harmonic in closed pipe is always this. Let's go through. The first one is like this. The second one let me produce just a sketch. A mere drawing. So the second one is like this. If there is no end correction. So over here, the length L2 is equal to 1, 2, 3, 3 on 4 lambda. Okay. Now, if there is end correction, the antinode goes beyond this. Immaculate, mute yourself. So if there is end correction, we have this. Okay. From the end of the pipe or the resonance tube to this end, we have E. This is the length of the air column. End of the length of the air column L2. So in this case, the equation would become 3 lambda on 4 is equal to L2 plus the end correction. Okay. Now, depending, we can compare first and second position of resonance to determine an actual value or exact value for the velocity of sound in air. We can also use one. It depends on the question. If the question gave us only the fundamental frequency or the first harmonic, then we'll only use this. If the question gave us 2 positions of resonance, then we'll compare this and this to determine the velocity of sound in air. Now, let's look at if it is any of these situations, how do we calculate for the velocity of sound in air, that constant value? So if it's about 1 position of resonance, maybe the fundamental, just this, then because quarter lambda for only 1 position of resonance, meaning I'm giving either one of them, first harmonic or fundamental frequency or any other harmonic. How do I use this to determine it? So from the relation, if there is end correction, we know that quarter lambda is equal to L1 plus E, where 1 represents the length of the air column which resonated with the tuning fork. So lambda is equal to 4 L1 plus E. If lambda is equal to this, then velocity of sound in air, which is F lambda, okay, V will be equal to F times 4 L1 plus E. Hence, velocity of the approximate value becomes 4F times L1 plus E. This will be the expression for the velocity of sound in air, where F is equal to the frequency of the tuning fork. Frequency of the tuning fork. I said a tuning fork gives just a fixed frequency. So this F here represents the frequency of the tuning fork. L1 represents the length of the air column which caused resonance. So you are varying. So as you vary, there will be a particular length of air column which will cause resonance. And then E is the end correction, which can be given in a question. If you are given two positions of resonance, this will give sort of, this is like rough value, approximate value. But when you compare two positions of resonance, it gives you exact value. It minimizes the error in this. So if I'm using two positions of resonance, this is how to calculate for the velocity of sound in air. The first resonance is giving me quarter lambda is equal to L1 plus E. Equation 1. Then the second position of resonance is also giving me 3/4 lambda, which is L2 plus E. That is equation 2. If we subtract equation 1 from equation 2, subtracting equation 1 from 2, you have L2 minus L1, the E will cancel out. So we have 3/4 lambda minus quarter lambda. This is equal to 4/2 lambda. And this is lambda on 2. So we have lambda on 2 is equal to L2 minus L1. Therefore, lambda is equal to 2 times L2 minus L1. Once you have lambda value, then the velocity of sound in air is equal to F times lambda, which is 2 L2 minus L1. L2 minus L1. Therefore, you have 2F times L2 minus L1, giving you the velocity of sound in air. And this, when you are given two positions of resonance, the value of this is so accurate, okay, than when you are giving one. Okay, so this is more like the actual, whereas only one is an approximate value. The level of accuracy here is greater than when you are given only one position to estimate the fundamental frequency. Please, any question? Any question? Oh yeah, Ekuya and Co. Any question? Yara. Another trick.
Sir,
Yes, sir.
sir, please, I have a question.
Go ahead.
Sir, please. So, apart from the first position and the second position, can we have any more other position?
Either you are given one or two positions of resonance. So it can be either one or two, 3 or 4. Okay. They can't give you 3 positions of resonance. Either they give you one to calculate to determine the velocity of sound in air, or 2 positions of resonance. But 2 positions of resonance can be the fundamental and then the second harmonic, or second harmonic and third. It depends on the question. Are you okay?
Yes, please.
Another trick which you can use is that I think in our next meeting, we'll look at how to use this to answer the practical question. You see, we had good. We had L1 plus E to be equal to quarter lambda. L1 plus E to be equal to quarter lambda. And L2 plus E also equal to 3/4 lambda. Now, this is one other thing we can do. When we take L2 plus E over L1 plus E, this is equal to 3/4 lambda times or divided by quarter lambda. This will give us L2 plus E on L1 plus E equal to 3 on 4, 3/4 lambda times 4 on lambda. This and this will cancel, this and this will cancel. So it means L2 plus E over L1 plus E is equal to 3. Okay. Therefore, L2, if we make L2 the subjects, we have L2 plus E equal to 3L1 plus 3E. L2 is equal to 3L1 plus 2E. Now, the value of E, the end correction, is usually very, very small, about 0.6 of times the diameter of the resonance tube. Now, what this means is that if I know the first position of resonance, which is L1, to determine the next position of resonance, it will be a little greater than 3 times the length, the first resonance length. So assuming I conducted the experiment, got L1 to be 30 centimeters. By this relation, it means that L2 will be a little bit greater than 90, because this is 3 times 30 plus 2E. And 2E is very, very small. So it means L will be around 90 plus something. So if I want to quickly do this experiment without wasting time, once I have this, I can easily get the positions of resonance. Okay. Once I have the first one, then the second one will be a little greater than 90. So all that I do is that I just open the tap so that the water will drain to close to 90, because that is, by the relation, that is where the second position of resonance will be. So if you have this, you can easily estimate the second position of resonance so that you reduce time wastage. Okay. So this is the whole nitty-gritty of resonance tube experiment. If you have any question, ask. If you don't have any question, let's quickly apply this in solving problems or questions. How do we apply this in solving of questions? Okay, so I'm reading. I'm giving you a typical question. A tuning fork of frequency 250 hertz. A tuning fork of frequency 250 hertz gives the first 2 resonance lengths of 33 centimeter and 98 centimeter. A tuning fork of frequency 250 Hz gives the first two resonant lengths of 33 centimeter and 98 centimeter when placed near the open end of a closed tube. Near the open end of a closed tube. The closed tube represents the resonance tube. Determine the velocity of sound in air. Determine the velocity of sound in air. Here, you are not giving end correction. Determine the velocity of sound in air. So, 5 minutes. Let's see what you can produce. Then we solve it together. I want you to try.
Mr. Dia,
Hello.
please can you send the question to the group?
No. A tuning fork of frequency 250. So the frequency is 250 Hz. Gives the first two resonant lengths. So L1, 33. L2, 98. And look at something. I said that L2 is equal to 3 times L1 plus 2E. So this is, if this is 33 times 3, 99. Okay. Well, theoretical value, right? It should be a little bit greater than that. Less or greater, right? So it's still within. Okay, so if you have it, to find it, all that you need to do, okay, let me multiply it by 3. Drain the water till it's gets to 99. Then you hear that the second position of resonance there. So when placed near the open end of a closed tube, determine the. So knowing that L1 is equal to quarter lambda plus L1 plus E is equal to this, and L2 plus E is also equal to 3 quarters lambda. And then L2 minus L1 is giving us half lambda. Therefore, lambda is 2 L2 minus L1. P will be equal to F times 2 L2 minus L1. So usually if you have gone through the theory and you know this relation, you quote it direct and do it. Okay, and that would save you from deriving as I'm doing. If you remember that the first, second position of resonance will be this. Second, third will be that. Then you write it that straight away and then use it. So 2 times the frequency, which is 250. Okay, 98 minus 33. This is 500 times, what is 98 minus 33? 55.
65.
65. And when you multiply this, you get what we had in centimeter per second. But when you convert 65 to meter and use it, then you have it in meter per second. Are you okay?
Sir.
Hello.
Sir, please, what does the E stand for?
The end correction. But when you subtract it, it will cancel out. E minus L2 minus, it will cancel out.
Oh, okay, okay.
Okay, another question. Another question. A tuning fork is placed near the open end. A tuning fork is placed near the open end of a resonance tube. Of a resonance tube, given the first two resonant lengths, given the first two resonant lengths of 23 centimeter and 58 centimeter respectively, given the first two resonance lengths of 23 centimeter and 58 centimeter respectively. Now, given that sound travels in air, given that sound travels in air at a velocity of 350 meter per second, given that sound travels in air at a velocity of 350 meter per second, what is the frequency of the tuning fork? What is the frequency of the tuning fork? This time, it's about the frequency of the tuning fork. And I want you to go through the theory, derive L1, L2, subtract, so that you'll be familiar with how to derive the relation before finding it. So, 5 minutes.
So please can you read the question again?
Pardon? Akuya,
Can you please read the question again?
a tuning fork, let me take a shot and put it into the group. So a tuning fork is placed near the open end of a resonance tube. Given the first two resonance lengths of 23 centimeter and 58 centimeter respectively. Given that sound travels in air at a velocity of 350 meter per second, what is the frequency of the tuning fork? So this time it's about the frequency of the tuning fork. So we know V first two. For first two resonant position, there is it. V is equal to 2F L2 minus L1. Once it's about the first two, when we go through the theory, we'll get this. So you must understand if it's maybe second and third or third and fourth and all that. So F here will be equal to V over 2L2 2 times this minus L1. So 350 over 2 times L2 minus L1 is 58 minus 23. This is 5. This is 3. So 0.35. Multiply 0.35 by 2 and divide your answer by 350. Okay. See, 350 divided by and is equal to 500. Okay, are you there?
Yes.
All right. So work on the one I've sent to the group. Area say. V is directly proportional to the square root of temperature. Meaning that when temperature increases, velocity of sound in air must also increase. Meaning that it also means that in the day, sound must travel at a greater speed than in the night. But does it work like that? Gerard?
Yeah.
This relation,
Sir.
this relation means that when temperature increases, speed of sound in air must also increase, implying that in the day, sound must travel faster than in the night. But does it work like that?
Sir, no.
Why?
No, it doesn't work like that. Sir, this is due to refraction of the sound waves.
Explain to me.
You see, when during the day, the sun shines, and so when it shines and it falls on the surface of the earth becomes hotter.
That's
And
why
it becomes hotter than the
that's why temperature in the morning must be greater than in the evening, because there's sunshine. Then we expect that
when the
sound travels faster than in the day than in the night, but it doesn't work like that. Why?
because of the refraction of the waves.
How? Explain.
When the sun shines, when the sun shines, you see that the surface of the earth becomes hot.
Yeah.
And so as it becomes hot, there are layers of it makes the this one like a little dense. Do you understand?
I'm following what you are saying.
Okay, so when it hits the surface of the earth, it becomes dense. So the down one becomes less dense, and then the top one becomes
Meaning the air layer,
more dense.
the air layer becomes
at the top.
Vary in density.
Yes, sir. So when you speak, you see that when you speak and then it goes into the air, some parts is more denser than the other. The lower parts are less dense than the top. So when you speak, it will refract
And
bending downwards.
and divert the path. Is that what you're saying?
Yes, and divert the path. Yes, sir.
That
It will
is,
divert the path downwards.
I get you. That is one aspect of it. But the other aspect is also due to interference. Okay. Yes.
Yes, sir.
During the day, the air varies in density as we go up. So there's refraction of sound. But it's also because of interference. You see, mostly due to interference. This is because during the day, you see, there are a lot of sound. The horns of vehicles, I mean, stone quarry, cars moving, people talking. So the interference is so much. And so when you send sound wave, it's like a battle. So the battling with other nuances or noises does not enable it to move faster. It is like you trying to move, okay, among a lot of people. You have a lot of obstruction. And so the speed with which you get to your destination is not like that. In the night, is the opposite. In the night, your refraction is not there. Aside the refraction, interference from other sources of sound is minimal. People are asleep. Cars are not moving. Birds are sleeping. The church or a lot of sources are not there. So it may sound as if in the night, sound travels faster than in the day because of this reason. But ideally, sound must travel faster when the temperature is higher than when the temperature is lower by this equation. Please, is that okay? So for two different temperatures, V1 over V2 would be equal to T1 over T2. So this is how to calculate velocity of sound in air as the temperature varies. Now let's elaborate this. So if we have two different temperatures for two different temperatures, T in degrees Celsius and a temperature of 0 degrees Celsius. Okay, it means that we have V1, Vt over V at 0 being equal to square root of temperature T in degrees Celsius and then temperature 0 degrees Celsius. Now we want to do something. Let's change these temperatures to Kelvin. Tk relates to Tc by 273 plus Tc. So a temperature T change to Kelvin, T in degrees Celsius change to Kelvin will be 273 plus T over temperature of 0 degrees Celsius change to Kelvin will be 273. Are we okay here? There's the temperature in degrees Celsius. So we are only converting these two temperatures in Kelvin. Please, are we okay here?
Yes, please.
All right. So we have, when we divide through by the denominator, we have 1 plus T in degrees Celsius divided by 273. Okay. Now let's expand this. Raised to the power half. Using binomial expansion, we have Vt and then velocity of sound at 0 degrees Celsius as 1 plus, when we use binomial expansion, 1 plus x to the power half. 1 plus half times x. Okay, the two larger terms, we are only interested in the two larger terms. Okay, and then eliminate the rest. So this will be half times T over 273. The rest will be smaller. So we want to end at the two larger terms. Okay. I know, so plus dot dot dot, but we want to end at just the two larger terms. So this is equal to 1 plus, please multiply this by this and then divide 1 by the results. 2 times 73, but let's change 1 over 2 times 73 to decimal. Quick one, quick one. Adwa and Co. Quick, Akpia. Well, you're no more.
Yeah.
You're no more nyadi and ten. Okay, so when you change this to decimal, this is 0.00. So we have this as 1 plus 0.00 1832 T. 1, 2, 3. Now, velocity of sound at a temperature of 0 is what we approximate as 350 or 330, depending on whatever you are given. Don't forget, here we were in the questions we saw, one of it, we were told that the velocity of sound in air is 320. So if it's 320, depending on whatever you are given, we'll have this as Vt over 320 will be equal to, so Vt will be equal to 320 times 1 plus 0.00183 T. When we multiply through by 320, we have 320 plus, multiply 320 by this for me, the coefficient of T. Multiply 320 by the coefficient of T for me. Who is doing that? Oh, who is calculating for me?
Zero.
Approximate your answer to 1 dp.
0.6.
So this is 0.6 T. So this is the relationship connecting a temperature Vt and a temperature 0 degrees Celsius. What this relation means is that velocity of sound depends on temperature by this relation. meaning that at every 1 degree change in temperature, the velocity of sound in air changes by about 0.6. Okay, so when the temperature varies by 1 degree, T is represented by 1 degree. And what would be added to the velocity of sound in air as a result of the change will be about 0.6 added to this. Okay, when the change in temperature is around 2 degrees Celsius, you have 0.2 times 2 added to 320. So this is the relationship connecting velocity of sound in air to temperature change. At every 1 degree Celsius change in temperature, the velocity of sound in air increases by 0.6. That is what this relation means. So this implies that at every degree rise or change in temperature, the velocity of sound in air increases by 0.6. Okay. So that is the relationship between the two. Any question? No question. If there is no question, then
Sir, please a question.
quick.
Sir, please, so the 0.6 that it will be increasing by, that is with respect to the velocity, the V not being 320.
As for this, it is constant. When temperature is at 0 degrees Celsius, okay, this is the velocity of sound in air. So when the temperature changes by 1 degree, this is what will add to this. So when it increases by 1 degree, T is equal to 1 degree. So the total velocity will become 320 plus 0.6. So this is what will add to this. When the temperature changes by 2 degrees, T is 2. 0.6 times 2. And so that would add to 320. That's what I mean. Are you okay? Immaculate, are you okay? All right. So next week, we have Doppler effect, and we'll start. Sorry, I said Friday. We have Doppler effect to look at, and then start a new topic. I want us to